VP, would like to introduce Mr. Rushikesh Gunjal. He is alumni of our institute. He is delivering the lecture or session on electricity demand of large language models, evaluations, challenges, and solutions. Mr. Rushikesh is a skilled DevOps engineer with over 3+ years of hands-on experience in building scalable cloud-native infrastructure and automating complex deployment systems. He specializes in Kubernetes platforms, AWS cloud services, CI/CD pipelines, and systems automation. With strong foundations in Linux and networking, Rushikesh holds a master's degree in management information systems from the University of Buffalo. It is University in New York, USA, with an outstanding GPA of 3.8 out of 4 and a bachelor's degree in mechanical engineering from Nutan Maharashtra Institute of Engineering and Technology, Pune University. He is currently working at the Pacific Northwest National Laboratory, where he designs Kubernetes-based data pipelines, PostgreSQL deployments, and automated backup systems for high-performance computing workloads. His expertise includes Terraform, Ansible, Helm, GitLab CI/CD, and Kubernetes automation for secure and reproducible infrastructure. Earlier at ConsultAd Incorporation, he created production-grade EKS clusters, optimized CI/CD workflows, and automated cloud operations, improving deployment speed and reducing operational cost. He has strong command over AWS, EC2, EKS, VPC, Lambda, CloudWatch, Python, shell scripting, and modern observability tools like Prometheus, Grafana, Datadog, and Splunk. Rushikesh has led several automation initiatives that reduce manual workloads by over 70% and significantly improved system reliability. He is also an AWS certified solutions architect and deep experience in secure, cost-optimized cloud design. On behalf of all the participants and organizing committee, I welcome Mr. Rushikesh for today's expert speaker for this ATAL online faculty development program. Welcome, Rushikesh, and over to you.
Yeah, thank you, sir, for a generous introduction. So I'll quickly share my screen. I think this was a pretty good and brief introduction, so I would not have anything to add on that. I'll share my screen. Yeah. Okay. Okay, I think you are able to see my screen now.
Yeah.
Yeah.
Okay, nice. Thank you. Okay, so let's start. I think hello everyone. Thank you so much for joining the session and giving me this opportunity to present one of the ideas and one of the things that I'm recently working in PNL, and I've been researching about it a lot. Is that so today we'll explore, the most important and rapidly evolving topic, that is AI, and how AI is consuming more electricity than any other system that has been designed in the history of human revolution, and how is the consumption being rapidly growing, and how are the these large language model consuming electricity at a very high scale. As LLMs continue to grow in their capability, the discussion often this discussion would often focus on modern performance and safety, but behind all this, it's a very real and physical foundation, that is electricity. Training and deploying this model creates power loads that are reshaping data center design, hardware engineering, and even regional grid planning. So over the next hour and a half or so, we'll break down the full electricity life cycle of these LLMs and look at the challenges and solutions that lie ahead for these LLMs. So yeah. Okay. So here's the roadmap. We'll begin with the motivation, like why electricity demand has become a central issue as AI scales. Then we'll examine the overall life cycle, how training electricity differs fundamentally from inference electricity. We'll walk through the methods used to estimate energy and emissions, and then discuss the key challenges across models, hardware, data centers, and power systems. After that, we'll try to shift into the solution space a little bit, everything from algorithmic efficiency of the grid aware deployment and clean energy sourcing. And finally, we'll wrap up the forward um, with a forward looking perspective on how LLMs can grow sustainably in the future. Um, yeah. So again, LLMs basically are the brain of the whole AI system that has been being evolving for the last 2 to 2.5 years. They require really substantial energy both during training and inference. Training involves an extremely power intensive workload that runs for weeks or sometimes even months. In terms of OpenAI, they have trained their models for like several months across, and they have consumed a lot of electricity in consuming so much data to have such big LLM models. We'll look into the LLM, the size of the LLM models and the evolution of GPT LLM models over the past and currently in the future as well. And inference, on the other hand, is lighter but occurs on enormous scale, billions of queries per day globally. As you can tell with the usage of OpenAI and ChatGPT across the world, the inference has been exploding in enormous packages, I would say. Um, as LLMs adoption scales across industries, the accumulated electricity used in becoming significant enough to influence data center explosion, coding requirements, and even local grid capacity. Understanding this demand is crucial not only for environmental reasons but also for cost planning and long-term AI sustainability. We have to make sure that we understand this, usage of electricity as well as how to control it, how to make it efficient, so that um, its adoption is easy for the future purposes that will keep on increasing enough. So it's really important right now for us to discuss on these things. Um, so I have always picturized the reason of putting these brain images for the LLMs is I've always picturized LLMs as brain. As human brains have evolved over the years, like LLMs are also evolving rapidly. This slide shows how rapidly the model size has grown. We have moved around 100 million kilometers in early models like BERT to over a trillion in the models like GPT-4, and now it's been like over 1.5 trillion more parameters for GPT-5 and GPT 5.1 as well. So the scale is not just a matter of adding more weights; it results in huge increases in floating point operations and training data volume. Since electricity demands scales with compute, each new generation of model tends to require significantly more energy unless major efficiency improvements are introduced in those models. This is why conversation around LLM power usage has become so urgent these days. Um, so training and inference behave very differently when it comes to electricity. Training is a high power, long duration process. It's predictable, scheduled, and extremely high intensive while it runs. Inference, on the other hand, is much light per request, but the sheer number of queries, especially with the consumer facing LLMs like GPT, Gemini, causes cumulative inference electricity to surpass training very quickly. So for popular models like again GPT, Anthropic, Claude, and Gemini, the total inference energy often exceeds the training energy within the days of deployment. We have seen that the ChatGPT image generation got really popular in India, and the inference and the electricity that was consumed by these models were literally exploding within days. This distinction is crucial for planning data center capacity and evaluating environmental impact of these particular models on. So, to understand the estimate of electricity use, we rely on few standard metrics. First is training tokens, determine how long the model is trained. Second is parameter count, which affects the compute required per token. Total flops, given a theoretical measure of the amount of the work done. Hardware performance, so flops per second. Let's tells us how quickly that what executed, and PUA accounts for facility overheads like cooling and power delivery. Together, these metrics allow us to compare training runs, hardware choices, and data center designs in more standardized and scientific way. So, uh, yeah, so the primary two ways of quantifying training electricity are: one is direct measurement using GPU or TPU telemetry to measure power draw in real time. This is the most accurate when available. The other is flop-based estimation, where we calculate the theoretical compute workload and convert it to electricity using hardware efficiency numbers. This method is widely used in research because telemetry data is open proprietarily. Both methods reveal the same trend. Model LLMs training typically consumes hundreds of megawatts of hours of to tens of gigawatts of hours of electricity. Um, so the modern architecture plays a direct role in demand. So transformer designs vary, encoder, decoder models, decoder only models, and newer attention mechanisms are all different compute costs. So every different model is structured in a different way, and this results in different types of energy consumptions across different models for different companies. Techniques like group query attention, sparse attention, or mix of experts architecture reduce how much compute each token requires. This architecture decisions meaningfully impact the power draw of both training as well as inference. So, in other words, architecture is not just the model quality; it's also a major level of energy efficiency in these models. Um, scaling laws show that reducing model error often require disproportionately more compute. This means that electricity demand doesn't rise linearly as models grow; it rises much faster. So, as models grow, so if the model is growing by 1x, usually the electricity demand for that particular model grows by 1.5x for 2x, 3x, depending on the size of the model. If it is training, and depending upon the number of customers that the model is facing, like GPT-4 can face ChatGPT can face more customers and it can require more electricity, whereas Gemini initially used to require less electricity, but now the demand has now exploded for Gemini as well. So Gemini also requires more electricity. So every time we push for larger context windows, more parameters, or better reasoning ability, every time we try to increase one more property about the models, the energy cost increases significantly unless offset by any efficiency techniques, which is rare these days. Understanding this scaling is essential for anticipating future electricity needs. Um, so to put scale into perspective, GPT-3, which was really popular in 2022, at the end of 2022, required roughly 3.7 into 10 raised to 3 flops, corresponding to over a gigawatt hour of electricity. GPT-4 requirements were far higher, estimated in the range of 51 to 62 gigawatt hours. These numbers make it clear that LLMs training is no longer just a computational challenge; it's an energy and infrastructure challenge as well. As models continue to grow, planning for the electricity footprint becomes just as important as planning for the arithmetic algorithmic design as well. So So this tells us that in the future, if we are looking forward for AGI to take over, and for our models to get more and more smarter and more and more efficient to do in our task, we need to plan ahead for the electricity consumption that is being required for training these models. Um, so when we talk about electricity consumption, it is not enough to look only at the GPUs. Data centers add their own overhead or to cooling, power distribution, and conversion losses. This is captured by PUE, which stands for Power Usage Effectiveness, which tells us how much extra facility power is required for per unit of IT power. So a PUE of 1.2 means for every 1 kilowatt hour used by the GPUs, the facility consumes an additional of 0.2 kilowatt on top. Similarly, carbon intensity varies dramatically by region. Running the same model in the coal-heavy region grid can produce 5 to 10 times more emission than running in a renewable or nuclear energy-based grid. This is why location also matters, as well as the hardware when assessing AI's environmental impact. So, to just give you a perspective, in the United States, the government has largely launched the projects for hydroelectricity, in United States it's not really possible for solar electricity, but they have been really pushing for wind energy as well as the hydro energy power plants to make sure that we have they reduce their dependency on coal heavy grids, whereas in India we can always focus on solar power electricity to make sure that our carbon intensity uh, stays as low as possible. To dive a little bit more in carbon emissions, so carbon emissions are a direct function of electricity consumption multiplied by grid carbon intensity. For example, just to give you an example, GPT-3's training generated an estimated of 552 tons of CO2 equivalent, largely because it was trained on a grid with relatively higher carbon intensity. But in contrast, Bloom, which is a very popular model by Bloomberg, was trained predominantly on nuclear power French infrastructure and saw emissions more than 20x lower for a compatible amount of compute. This highlights an important point. Energy consumption is one thing, but carbon impact depends heavily on where and how the electricity is being produced. This slide gives an estimate of the sense of scale. GPT-3 consumed an about of 1,287 megawatt hours of electricity. Estimates for GPT-4 are dramatically higher, between like 52 and 62 gigawatt hour, depending upon the consumption, about hardware efficiency and cluster topology that is on which the model is being deployed. This massive jump illustrates how quickly the energy requirements grow with the model side. It also demonstrates why is efficiency important in hardware and algorithms are now a hot topic to discuss and not an optional topic anymore. Um, Another example of Meta, who is a very popular and a key player in these LLM race. It has like Meta models are usually use a useful comparison because they are trained on the same A100 cluster. The 7 billion parameter consumed about 74 megawatt hours, while the 70 billion model required about 660 megawatt hours. Interestingly, the
हा डॉक्टर
growth isn't
आवाज येत नाही.
purely
किती
sorry.
वाजता?
Interestingly, the growth
ओके.
isn't purely linear. Meta used
आहे
efficiency
छोटा
optimization
होतो
such
मध्ये.
as better parallelism and training pipelines, which help moderate the increase. This shows that the smart engineering and can sustainably reduce even when scaling up the model size. So Meta has been really keen and really you know concentrating on like how they can efficiently train their models. Um, And another example of Google GLAMS model is a great example for architectural efficiency. Instead of activating all parameters for each particular token that was trained, GLAM uses a mixture of expert design that activates only a small subset. This means the model can have a very huge parameter count. In this case, about 7 times larger than GPT-3, ChatGPT-3, while consuming less electricity during the training. MOE architectures demonstrate that scaling doesn't always have to come with a proportional energy cost, provided the architecture design is designed very intelligently and efficiently. um, Fine tuning as well as few training. So, not always you would fully train a model. There are very few companies who are fully trained model from scratch, such as ChatGPT, Gemini, then there is Grok, then there is Anthropic models. These are only, and I think there is open Facebook's Llama model. So these are only 7 to 8 models which are um, trained from scratch. But other than that, any company that is using their own models are not really using their own model. They're fine tuning their model. What is fine tuning? Fine tuning basically is like runs for hours it runs for hours instead of days or week, and in most cases it consumes well under 1% of the electricity that is required for original training run. So what it does, it takes the original train model, and then you train it according to your purpose. Let's say ChatGPT is trained for all general purpose uses, and I want to develop an application for hospitals, right? And for the hospital data or medical data. So what I'll do is I'll take the ChatGPT model, I'll fine tune it according to my needs. I'll just fine tune or I'll just trigger those areas in the model that are related to healthcare and health infra that are needed for my cases, which then eventually gives me an advantage of not training the model from fully and have the expertise and coverage of the whole model as follow. And again, it reduces my consumption drastically. This is why I think pre-trained models are so impactful. They allow developers for achieve strong performance with incredibly low marginal energy cost. Uh, so again, inference energy, while training is a large one-time cost, inference is continuous. So every prompt typed into an application powered by an LLM creates an incremental energy cost. So every time we do a chat GPT query, there is a energy cost that goes into that particular query. And depending upon the complexity of the query that we have, let's say you say, what is my name? That would have a really small energy impact. But if you give a calculus or a derivation problem or an integration problem to solve to a chat GPT, a very complex integration problem, it would require the GPT model to churn a lot more in energy for that particular query. And as LLMs are adopted across search, customer service, often software, and multimodal applications, the number of daily inference calls has been exploding. For larger user bases, inference electricity quickly becomes the dominant contributor of total life cycle energy. And so that's why understanding energy is therefore inference energy is really essential for evaluating long-term operational cost and the environmental impact that it does. Um, so inference energy workloads fluctuate based on user traffic always. They are bursty. So you can have really low energy consumption at, let's say, 1 a.m. in the morning, but really high energy consumption at 12 p.m. or 1 p.m. where in during the business hours. So during peak times, accelerators run close to full power. During slow periods, they might sit idle. However, idle GPUs still consume a non-trivial amount of energy. This makes estimating inference energy very tricky. Using training time peak power as a proxy for inference usually overestimates the demand. Conversely, ignoring idle time consumptions when the model is idle and when there is no one using it. So accurate modeling must consider utilizing levels, queuing delays, and batch sizes in which the queries are being served, which vary widely across real world deployments. Um, so inference energy also depends on one very important thing heavily on a task. A simple classification request might use 0.002 megawatt hours, sorry, watt hours, whereas text to image generation can average around 2.9 watt hours, a difference of more than 3 orders of magnitude. Multimodal models tend to be more electricity intensive because they have larger tensors, more parameters, and deeper compute pipelines. This means the type of application dramatically influences the overall electricity footprint. So, again, give you a short example. If you chat with ChatGPT and have a text-based prompt, it would consume a lot less electricity as compared to you trying to generate a complex image, or you trying to generate multiple images through ChatGPT. That would have a really, really high electricity footprint. Um, again, to dive a little bit more deeper, like continuing the idea, text-based inference is relatively higher lightweight compared to multiple inference. Models that generate or process images, video, or audio require substantially more compute per request. As product ecosystems shift toward multimodal AI, for example, models can now analyze images, generate artwork, process videos, edit videos in like live streams. The electricity demand per inference has increased significantly. Understanding these distinctions helps organization plan infrastructure and optimize model selection based on the use cases. And according to my experience, so in like I have been working with consultant, and um, there we used to work on a cloud-based model where we used to get compute and electricity based like on demand, and we used to pay the price of on demand electricity. But now in PNL, which is a government based organization, the usage of cloud is really, really low because of data sensitivity about the Department of Energy, US Department of Energy data. That's the reason we are generally using on-premises systems. And here, while we fine tune our models, we usually fine tune our models, and training, fine tuning text intensive models are really, really easy and less energy efficient, less energy consumption, while the multimodal models consume a lot more electricity. And for us, we have to plan that requirement of the systems like before the work even starts, to make sure that we meet the consumption requirements. So it's a very practical way of thinking into how we can plan efficiently for the future purposes. Uh, as we scale up from individual inference calls to global usage, the electricity footprint becomes large very, very quickly. So with more than 10 million daily ChatGPT users, and this is a very old data that I was able to get. I was not able to get the exact amount of data that ChatGPT 5.0 user, but this is a ChatGPT 4 data. The cumulative daily inference can exceed up to 560 megawatt hours. That means that a single week of inference traffic can use more electricity than that was used for training the entire run of ChatGPT 3. This highlights the shift happening in AI consumption, that is, inference is more important, not training. And inference is increasingly the dominant driver of the two. And as models are deployed broadly across consumer products, the long-term operational energy is what truly defines the sustainable challenge for us. Um, the cost parity. This is the slides. I put this slide to illustrate a very key concept, cost parity, which is a point at which cumulative inference energy equals one-time energy. So for higher popular LLMs, the point arrives surprisingly fast, sometimes within just a few days or weeks of deployment. This reinforces the idea that energy story of LLMs is not about training spike alone. It's about continuous energy draw of several billions of queries over months and years. Managing inference efficiency is critical for controlling both electricity use and cost at scale. So it's really important for us to determine how our application is scaling, or at least predict that, okay, how can our application be adopted by users and how many users will it adopt. Will it be a regional application? Will it be a national application, or will it be a global application like ChatGPT? In according to the usage, or according to the customer base that the application would adopt, the energy consumption will increase drastically according to it, and will surpass the energy consumption that was required for training easily, or very quickly, respectively. So disparity in the energy estimates. So energy estimates for some model often differ by large margins. So this happens because different studies use different assumptions and system boundaries. Some include only GPU power, while other include CPUs, networking, or cooling overhead through PUE. So some count fine tuning and intermediate runs, others don't. Hardware consumption such as accelerate type utilization or flops are also widely used. This result is published. This result is that published estimates can vary orders by magnitude. This consistency makes it challenging to compare models fairly, or to form clear policy guidelines for usage. Um, uh, Building on the previous slide, like a little bit more into that, defining what counts toward energy consumption is more non-trivial. If we count only GPU power, we miss CPUs, storage systems, networking switches, and power conversion losses. Um, if we include data center overload, the POA dramatically changes the result. And if we include ancillary tasks like hyperparameter searches, checkpointing experiments, or failed run, the total electricity increases even more. This is why standard reporting frameworks such essential. Without consistent boundaries, comparison becomes like a misleading term. uh, Hardware and electricity variability. So hardware choice is one of the strongest determinants of electricity upgrading from older GPUs like V100, NVIDIA V100, to newer accelerators like the A100, H100, or the TPU V4 can improve energy efficiency by 30 to 80%. And most of the hardware experiments, or most of the hardware uh, advancement has all now been focused to how they can make the hardware more energy efficient. Um, Mixed precision transformer engines and architecture level optimization can also further reduce flops per token. But it's not just raw compute, memory bandwidth, interconnected performance between those GPUs, and activation sparsity are also important roles. This means that as our hardware evolves, the electricity cost for training and inference can drop substantially even for the same model architecture. So geographic power grid impact. So even if two data centers use the same hardware and run the same model, the carbon emissions can differ dramatically depending on the power grid, as I previously explained. A model trained in a coal-heavy region may have 5 to 10 times more emissions than of the same model trained during in train run in the region where it was powered by hydro energy or wind energy or nuclear energy. For companies running large training models, siting decisions, choosing over the run training are also becoming important as compared to algorithmic decision. Location is now a major lever for reducing these emissions. um, Challenges. The further of AI energy demand is uncertain because of the two opposing forces that are at play. On one hand, models are scaling rapidly. More parameter, larger context, multimodal capabilities. These trends they would drive energy consumption in the upward direction. On the other hand, efficiency improvements in algorithms, training pipelines, and accelerator hardware push energy demands downwards. So the net effect depends on which side improves faster. At the moment, both sides are improving quickly. and predicting large long-term electricity demands require careful consideration of both scaling trends as well as efficiency innovation. So we have to have the downward trend always in the superior ideally, but as of now they are like leveling. So the demand is also increasing and the efficiency of the models, algorithms, as well as the grid is also being increasing. So there is always we are always at the null point of the weighing scale. Ideally, it should be downwards. The efficiency should always surpass the in the consumption increasing of the consumption rate. But as of now, we are at the level, so I think we are good, and we are there is more work needed for sure. But yes, we are good as of now. Um, Modern accelerators. So modern accelerators are increasingly specialized for AI workloads. So the addition of tensor cores, transformer engines, and non-chip memory significantly boost throughput per watt compared to general purpose CPUs. So this specialization is one of the main reasons AI has scaled so quickly. Hardware has kept pace with those algorithmic advancements. So as a move into the Blackwell and TPU 5 generation, efficiency gains will likely continue, helping reduce the electricity cost per token. So that's the reason NVIDIA has been one of the popular names these days, because of this only, that it has been all constantly pouring money into experimenting on how we can make their GPUs more and more efficient and more cost efficient for the in terms of electricity consumption and the output that they give. Um, there is also being in data center power density. So AI clusters require far more power per rack than traditional enterprises data centers. It's now common to see AI racks draw 150 to 200 kilowatts each, compared to historical norm, which was like 3 to 5 kilowatt per hour per rack. So this shift requires a rethinking of data structure architecture, from electricity distribution to cooling systems. Many existing facilities cannot provide this kind of density without major upgrades. AI's growth is driving directly a new generation of density data center designs, which have these facilities included. Um, Extreme rack power and cooling. So, as power density increases, air cooling reaches its limits. TDP accelerators need liquid cooling or even immersion cooling to operate safely. Beyond thermal constraints, the physical architecture of the data centers, like floor loading, piping, electricity routing, must be adapted to support this extreme dense racks. Cooling is no longer just an operational detail or just a cool thing for a data center. It's a fundamental part now for enabling large scale compute. Without without the advancement of cooling technologies, next generation models simply couldn't be trained or deployed efficiently, or we can't consume electricity efficiently without having the right cooling techniques for those data centers. Um, uh, Grid limitations and power shortages, these are also one of the important factors. As workloads grow, many regions are running into infrastructure bottleneck, not inside the data center, but in the grid itself. Locations, very popular locations like North Virginia in the United States, Frankfurt, and Beijing are already facing delays in securing new grid connections, because the local substations and transformers are reaching their capacity, because they are not designed for those electricity consumptions or to adapt to those high electricity consumption. This means that even if companies want to build new AI data centers, they often don't get the necessary electricity capacity approved. AI growth is beginning to collide directly with AI grid constraints, creating a need for a new investment in transition lines, substations, and long-term energy planning for these in the especially in the towns where the data centers will be deployed. Um, Regional rallies and countries, these are also one of these important factors. In response to these pressures, some regions have introduced special tariffs and contractual requirements for data centers. These tariffs often require data centers to pay a larger portion of their contracted power capacity even when they are not using it. The reason is very simple. I think power infrastructure must be built to support peak loads, and grid operators need a stable revenue to justify those investments. For AI operators, this creates financial incentives to optimize utilization, flatten peaks, and avoid over provisioning. Electricity planning becomes not, I think, not just a challenge, but like an economic. It's an economic challenge as well, for sure. Environmental impact and CO2 growth. So data centers have already like account to roughly 1 to 2% of the global energy electricity consumption, and about 1.4% of the global CO2 emissions. With AI workload scaling, their share with those totals are really rising to a whole new extent. If compute demand grows faster than efficiency improvements and cleaner energy adoption, emissions could continue to increase. This is why AI sustainability discussions often emphasizes not only on hardware efficiency but also on carbon consumptions of that particular grid. So that's why, and I think energy use itself isn't the issue. It's carbon intensity behind the energy, behind the electricity that is used to create that particular energy is also really important. Uh, Social reward effect. So again, there is also a social dimension to it. I think so. Energy gains can paradoxically increase overall energy consumption. This is known. This is a known. This is the known rebound effect. So as models become cheaper to run, more individual companies use them more frequently. This can lead to net increase in total electricity consumption, even as per query energy drops. So understanding the rebound effect is really essential because it affects long-term forecasting. Efficiency alone isn't enough, I think. Usage patterns must also be considered very well. So just to give you a short example, let's say I am ChatGPT. I have trained and deployed a GPT-4 model, but now in my area where I have deployed, there are 3 4 more companies who have now started to use my model and build their applications on top of it. So now, let's say I shift to a mayor of that particular city where these 4 companies data centers reside. Um, on paper I see that okay, ChatGPT has increased their efficiency per query, but now the usage has also increased dramatically because there are 4 more companies using my model. So forecasting that, it's a really tricky situation. It needs to be considered for the longer term purposes when it comes to grid planning and electricity planning, as well as the impact that it creates over the long term. Uh, Substitution effects and effectivity gains. So on the other hand, I think LLMs can replace processes that are themselves carbon intensive. That's a key point to consider. For example, AI can substitute manual tasks, eliminate travel, optimize resource use, or automate a work that would have consumed more electricity before. So in these cases, the electricity used by model can lead to a net reduction in emissions across an entire workflow. So the impact LLMs isn't one directional. They can increase electricity use in some areas while reducing emissions in others. So a fully analysis must look in both sides of the systems and not just one side of the consumption side. Um, so a solution to address these electricity changes over LLM, we need a multi-layer approach, and this framework spans over 4 tiers. One is software and hardware design, improving algorithms, architectures, and accelerators. Two is data center architecture, so optimizing cooling, power distribution, rack density, and so on. Third is power grid and energy sourcing, so integrating low carbon energy and improving grid awareness and efficiently planning the grid. Like the grid efficiency for the future is a key point in that. And it's 4 is external evaluation and regulation. So creating transparency, reporting standards, and incentives for efficient in planning. So I think no one single solution is efficient. Sustainable scaling improvements across this is really important. All these 4 points is really important. So let's say software optimizations. On the software side, architecture techniques can dramatically increase the demand. We have seen approaches like mixture of experts activate only a subset of parameters per token, lowering compute requirements, and newer attention mechanisms such as multi-head latent uh, attention reduce the cost of attention computation. So let's say I picture this as your brain, right? You have different information is stored in different parts of the brain, and picture that. Okay, let's say I have to think about healthcare, and healthcare is on this side of my brain, right? So a multi head latent attention, what it does is it just activates those parameters or those side of my brain or those side of that parameters in the LLMs, and serves the query by just using that part of the LLM. So this dramatically reduces the efficiency or the electricity consumption that is required per query. Um, Training efficiency techniques. Again, training efficiency can also offer many opportunities for energy saving. Training techniques like mixed precisions, improved optimizations, better learning rate schedules, and reducing hyperparameter fees, shorten training time, and reduce total GPU hours. Even small improvements such as efficient batching or fewer trial runs can yield meaningful electricity reductions. Training efficiency is a combination of algorithmic insight and disciplined training, I think. So again, I think to give you a short example, so when I was training my model, I had like four tests or four parameters which I was testing on my model. So depending on the test, also the number of tests that I am number of tests that I am testing my models through also increases or decreases my consumption cost, or like the electricity consumption and the GPU consumption as well, that my model consumes. So it's really important to precisely endure the steps of the training as well. So uh, model compression and quantization. So model compression plays a huge part, I think, in lowering inference electricity. Quantization reduces numerical precision. Pruning removes redundant weights, low rank adapters. Shrink memory sizes, and distillation transfers knowledge from larger models to a smaller one. So again, ChatGPT can also have smaller models. So they have now started working on different models. So let's say you go on ChatGPT now and you see a different option like deep research, codex, then generate images. So these can be served through different smaller models or different models to make sure that um, um, you know uh, uh, to make a use of smaller and compressed models. So let's say they have, I think they have a 1.5 trillion model, and now they have smaller quantized models which serve different purposes and which serve different use cases. So the bigger model can decide which query should go to which quantized models, and they can then serve uh, which can result in lower electricity consumption per query, for sure. Uh, Parallel training strategies. So, to train very large models, we need to distribute work across thousands of accelerators. This requires sophisticated parallelism strategies. Data parallelism, tensor parallelism, and pipeline parallelism divide the model or the dataset in ways that keep each device fully utilized while minimizing communication overhead. So, well-designed parallelism doesn't just make training faster; it makes electricity efficient. Poor utilizations or excessive communication waste energy. So parallel strategies are crucial for sustainable large scale training. Fine-tuning efficiency. Again, the fine-tuning efficiency builds on the idea that every task requires retraining an entire model. Techniques like LoRa and adapter modules allows us to update only a tiny subset of parameters rather than the full network. This drastically reduces compute and electricity use. Instead of requiring thousands of GPU hours, fine-tuning can typically be done in on a modest hardware and often in matter of hours. I have fine-tuned my models on my laptop, so rather than using a full-fledged rack of CPUs, it's really easy to fine-tune models according to the usage. This is one of the most practical and impactful ways, I think, to reduce energy footprint of real-world AI development. Hardware optimization. So hardware, again, as we have discussed, hardware is evolving specifically to meet the needs of LLM models. Model accelerators includes specialized matrix units, large on-chip memory, um, and better data paths. So these innovations reduce number of off-chip memory operations, which are among the most energy-intensive parts of the LLM consumption. So co-designing hardware with LLM um, architectures enables significant reductions in electricity per token, improving both training and inference. Uh, custom accelerators such as Google's TPU4 or NVIDIA's Blackwell architecture pushed energy efficiency much more faster. So Blackwell, for example, promises 100 folds improvements in the training throughput and tens of thousands of folds of gains in increasing effectively relative to earlier GPU generations. So these accelerators are purpose built for transformer workloads, making them central to reducing the electricity footprints of the LLMs at scale. Uh, Processing in memory, I think energy demands of LLM. So processing in memory or PIM addresses one of the biggest bottlenecks in AI systems, I think. So the cost of moving data between memory and compute units. So by performing certain operations directly in near memory, PIM architectures reduce the need of expensive RAM transfers. So this can significantly cut electricity usage or for like computational needs or where memory bandwidth often dominates the energy cost. And I think for us, it can be negligible to transfer data from RAM to our ROM, but when it comes to like trillions of parameters and millions of petabytes of data, it becomes a huge difference when you transfer information or data from memory to like the compute systems. So it's really important for having in-memory processing, a really highly efficient in-memory processing for these GPUs. One of my favorite parts, edge and cloud to edge deployment. So cloud to edge architectures, not all inference needs and hyperscale data centers. Edge computing running models on local or distributed nodes can often offload traffic from central clusters. So this reduces the backbone energy use, improves latency, and can lower in operational costs. A hybrid cloud to edge strategy is becoming increasingly common, especially for applications requiring like fast response times or privacy sensitive workloads. So cloud has always been a norm, and now it has been evolving for the AI evolution as well. Distributing training advances. So as models continue to scale, distributing training becomes more complex. So advanced interconnected and high bandwidth networking and optimized routing algorithms are are essential to keep thousands of accelerators synchronized. So modern distribution systems used specialized file systems, hierarchical communication topology, and intelligent scheduling to reduce training time and energy. So the better the energy distributed strategy, the more efficient electricity is used during massive training runs. Uh, Edge inference gains. So edge inference isn't just about shifting where computation happens. It's bringing real energy gains. So running inference on edge often doubles throughput, reduces latency, and cuts the energy overhead associated with um, the cloud side GPU optimization and data movement. So for workloads that are predictable or latency intensive, edge inference can significantly reduce the electricity footprint that is required for getting those calls in place. SLM deployment as edge. So small language SLM stand for small language models, such as Phi 2 or Gemini Nano, are designed to run on phones and laptops and other consumer hardware. So when these smaller models can handle routine tasks locally, so they reduce reliance on central data center inference, and this shifts a portion of electricity burden away from hyperscale clusters and reduces its like across millions of low power devices. SLMs are therefore a key part of making AI more efficient and broadly accessible. Physical architecture optimization. So, beyond chips and models, the physical power architecture of the data center plays a central role, as we have discussed in energy efficiency. Redesigning power topologies, using more efficient voltages, and reducing conversion stages can significantly cut losses. These improvements enable data centers to support high density AI clusters while also reducing electricity wasted during the power delivery as well. High voltage power delivery. So sorry, high voltage power delivery is becoming essential for supporting AI dense racks. So feeding racks with higher voltages such as 415 to 50 volt from 13 kilowatt feeders reduces current and cable losses and minimizes the number of distribution components needed. This is a key enabler for supporting racks that draw 100 to 200 kilowatt or more, which traditional low power, low voltage design simply cannot handle efficiently. AC to DC conversion and data center is also another important optimization is reducing the number of AC to DC conversion stages. So I think several servers operate on DC power, but the grid power is AC. So multiple conversions typically occur before electricity reaches the GPU. By shifting towards DC distribution, potentially combined with batteries and on-site renewables, data centers can achieve 10 to 30% of energy gains, which translate directly to low operating cost and less carbon emissions. Cooling optimization, we have discussed that cooling is one of the largest non-IT electricity consumers in the data centers nowadays. Advanced cooling solutions such as direct liquid cooling, immersion cooling, and AI-powered thermal controls dramatically reduce this overhead. So lowering the PUE if even slightly across a hyper AI cluster can save millions of kilowatts annually. As GPU densities rise, optimized cooling becomes essential not just for efficiency but for enabling safe operation as well. Low carbon integration, as we have discussed, is again to reduce emissions. Many AI operators are pairing their data centers with low carbon energy resources like wind, solar, hydro, and nuclear. Um, Localized clean energy reduces reliance on long distance energy transmission lines and enables more predictable and low power conversions. In the integrating low carbon sources is one of the most direct and impactful ways, I think, according to me, to decarbonize LLM electricity demand. Nuclear and renewable setting. Again, I have given example. I have given you an example of Bloom, which was a LLM model trained by Bloomberg, or has demonstrated the advantage of siting training models near nuclear plants, achieving order of magnitude in emission reductions due to the low carbon intensity of French nuclear power that they have used. So siting large AI clusters near clean energy hubs, near nuclear, hydro, or concentrated wind or solar energy regions, is increasingly seen as a strategic decision that shapes carbon impact more than any individual efficiency improvement. Grid-aware deployment is another emerging strategy that we have discussed. Instead of running models anywhere, companies choose deployment regions based on real-time or historical carbon intensity, capacity planning, and grid flexibility. So this ensures that the same workload can be executed with efficiently significantly lower emissions simply by being like scheduled at the right time or at the right location or time. It is a powerful example, I think, of how smarter orchestration can enhance sustainability without sacrificing performance. Uh, Carbon-free energy strategies. So many AI operators are adopting carbon-free strategies such as power purchase agreements, on-site solar installation, and a 24 by 7 carbon-free electricity commitments. So these approaches help offset or directly replace fossil-based electricity with clean energy sources. As energy demand grows, long-term carbon-free energy procurement is becoming um, a a core part of energy infrastructure, AI infrastructure planning, I would say. Uh, Regulatory and evolution framework. So, policy frameworks and standards are, I think, one of the most important parts that are taking place right now. They aim, I think, to require consistent reporting of electric usage, carbon emissions, and system boundaries to these companies. Cleaner regulatory standards help make sure like that is there is transparency and make it possible to compare models and deployments fairly. So over time, such framework I think will help us guide industry toward a more sustainable and accountable AI development. Benchmark and transparency again, alongside regulation, the community is also pushing standardized benchmarks such as flops we have discussed for efficiency, kilowatt hour per token that is there, and GCO2 per query. So, how much grams of CO2 emission is there per query? It sounded first for me like a silly metric, but now it does make sense when I went through data. These metrics makes us possible to evaluate and compare LLMs across architectures, hardware, as well as the deployment environments in which they are deployed. So improvement transparency drives better energy decisions and encourages competition between between these companies toward like efficiency rather than like just scale alone. Uh, Future outlook for LLM energy. So the future electricity demand will depend on the balance between scaling and efficiency. Compute requirement will almost certainly continue to rise, but rapid innovations in software, hardware, data center, cooling strategies, clean energy give us a realistic pathway to keep this particular growth sustainable. I think the challenge is very substantial, but so is the progress being made across these regions in this AI ecosystem. Uh, um, Conclude. So LLM electricity demand is both, I think, technological and environmental and an environmental challenge for everyone. But with coordinated advancements in algorithms, hardware, data centers, and energy sourcing, we can scale AI in a way that aligns with our long-term sustainability goals. So the path forward isn't about limiting AI; it's about building smarter and more efficient systems that allow AI to grow um, responsibly and sustainably. So it's a way forward for us to it's a good way to look forward in this adoption of AI. Um, uh, Training energy comparison. So this is a graph. This is just a graphical representation of what we have discussed so far. This shows a dramatic variation in training energy across major models. GPT sits at like 1,287 megawatt hour. Bloom around was 443 megawatt hour, and Llama models ranging of tens and thousands, hundreds of megawatt hours. But GPT-4 although proprietary is estimated in tens of gigawatts of hours. So this key takeaway again, this is a key takeaway for us uh, um, on how vastly depending on factors like model size, architecture, decisions, hardware generation, and data center efficiency plays an important part in energy consumption. Uh, One more diagram, I think so. Uh, yeah. So okay. Okay, so inference versus training share. So I think again, this shows, this slide emphasizes, and this shows the diagram of what we have discussed, that how one can be fooled that okay, training and be a major energy consumption, but as the models have increased, the inference energy has always been the major portion of the energy consumption as compared to the training share. So it's highly important for us to look into the inference and inference optimization in the future rather than the training share. And I have, I think, one more diagram. Yeah. So this is, I think, looking ahead to 2030, projections estimate that AI electricity demand could increase around to 4.3 gigahertz today to as much as 24 gigawatts by the end of the decade. So this doesn't mean AI will overwhelm the grid, but it does mean that energy planning needs to evolve rapidly to meet this requirement. Investments in grid infrastructure, clean energy, new cooling methods, new hardwares will essentially keep up with this, keep up with us with the AI growth. So these projections serve as a reminder that we must built in proactively and not just keep on adding stuff. So yeah, these are just numbers and projections. I have a reference to this particular Stanford paper for this particular presentation. Again, I would be really appreciating if you have any questions. I think that's it.
Yes, sir. Thank you for your nice presentation. Dr. Davas, sir. Dr. Davas, sir.
Dear participants, if you have any questions, queries, please ask to Mr. Rushikesh so that he can answer you. Even you can work with him regarding this energy related, how we can minimize the footprint of the this electricity usage. Yes, sir. I think the sir is
Yeah.
online. Yeah.
Am I audible, sir?
Yes, sir.
Yes. So thank you so much, Gunjan.
Yes, sir. Thank you.
So thanks to all the participants for patience learning and listening to Rushikesh, and he has delivered a nice session on electricity demand of large language models, evaluations, challenges, and solutions. And I think this session will help all the participants for their research as well as in academics. So thank you so much, Rushikesh. We'll be in touch in future also for the coming MTPs and other seminar and webinars. Thank you so much.
Thank you, sir, for the availability, and thank you for the audience for listening to me patiently for an hour. Thank you.
Yeah, thank you so much.
Thank you. Dear participants, now we'll have the break for 25 minutes. So we are again meeting at 6:30 for the validatory function of this online ATAL FDP. So I request all the participants to rejoin or to this validatory function so that we will grace our validatory function in a good way. Once again, thank you, and we are waiting for the validatory function. Thank you. So can you hear me, Davas sir? Hello, am I audible, sir?
Yes, sir.
Yeah, we'll join at 6:30, sir, for the valedictory.
Okay, thank you, sir.
Okay.
So you'll be joining at 6:30, right?
Yes, sir. Yes, sir.
Okay. I lost my connection.
Okay.
No
Okay.
problem. We'll be joining at 6:30.
Sir, just before that, you can just remind to the official bearers.
Yes, sir. Yes, sir.
Yes, sir.
I will.
And chief guest also, sir.
Okay.